Welcome back to the lectures on drone systems and control. In lecture 12, we will talk about one very important concept of control systems called transfer functions. It is very useful in analysis of systems, analysis of system response, then checking their stability, then accuracy and many other parameter and performance metrics. So, transfer function is a continuation. We need to study Laplace transform first, and after that transfer function becomes easier to understand. So, in this lecture we will define what a transfer function is, we will understand the derivation of transfer functions from differential equations. When a system is represented by some differential equation, then how we get the transfer function, that we will define here. We will apply Laplace transform for system modeling. It is when we talk about transfer function, it is a kind of direct application of Laplace transform in control systems. We will analyze transfer functions for drone system components, and then finally explore practical applications in drone dynamics and control. So, we can represent systems in different ways. In lecture 10 I was talking about differential equation, then transfer function and state space models, right. Now, in this lecture we will concentrate on transfer function. What is it? It expresses the system as a ratio of output to the input in Laplace domain. That means, if we have a system, say this is the system, we have some input say u t to the system and we get output y t, fine. Then the Laplace transform of u t is u s, Laplace transform of y t is y s, and if we take a ratio of output Laplace transform by input Laplace transform, then we get a transfer function. It is valid for linear time invariant systems. Okay. Fine. So, when we define a transfer function, it is a mathematical representation of relationship between input and output of a system. Which system? It should be a linear time invariant system, and this representation, that is the ratio of output and input, is in Laplace domain. Okay. It describes forced response, that means input output relationship assuming 0 initial conditions. So, a system can have two kind of responses. One is because of the initial condition it will give some response, and that is called 0 input response. Other thing is that it can have a direct input to the system, and what we get is 0 state response. At that point of time we do not consider the initial conditions. Okay. So, it is called 0 state, that means the initial condition or the previous states are 0. So, when it is initial condition based system, or we check the performance of the or the response of the system in terms of initial condition, then the input or forced input is 0, that is why we called it 0 input response. If only input is playing the role and no control or no initial condition, then it is 0 state response. Okay. Fine. Now, the mathematical expression or representation is something like this. Here we are considering that the input is r t, output is y t, fine. Where what is G s? G s is called the transfer function, that is the ratio of Laplace transform of the output and Laplace transform of the input. Okay. So, this is y s and this is r s, fine. Why do we use transfer functions? So, when we are having Laplace transform in our hand as a mathematical tool, we know that differential equation can now be converted to one algebraic equation. Now, when we do that, we get G s equal to y s by r s. So, the system representation gets easier. System must be linear and time invariant. Initial conditions are assumed to be 0. That means it is a 0 state response, or we can say it is a forced response. Okay. The transfer function is a frequency domain representation. What does that mean? We have S domain representation which has sigma plus j omega. Omega is the imaginary part of the variable S, and this actually represent oscillations in the system response. So, we are telling that when we talk about S, it is essentially a frequency domain representation, a kind of frequency domain representation. Okay. So, the purpose and the benefits of transfer function is that it converts differential equation into algebraic equations. It enables analysis of system behavior in terms of poles and zeros. I will define in the later slides in this lecture, and then it is useful for designing and analyzing control systems such as in drones, autonomous vehicles, etc. Okay. So, I will give one example first. Take a first order system. What is the order? I will come, but what is the order of a system? But we know that order of a system 1 means it can be represented as a first order differential equation, right. Now, if we take a Laplace transform with 0 initial conditions, that means forced response, then it becomes something like this, tau dyt dt. We have seen in the Laplace transform lecture that if we are taking the derivative of some signal, then it becomes of this shape. It gets multiplied by tau as a coefficient, then yt Laplace transform is ys, k ut Laplace transform is k us. What is ut? Ut is the input. Fine. If ut is the step input like this, here we are talking about a general input, but if ut takes the shape of a step input, then us will become what? 1 by s, right. Okay. So, solving for GS, now what we need to do is that we have to find this ratio ys by us. What is that? From this particular expression or equation, we see that the transfer function or equal to ys by us is equal to k by tau s plus 1. What is s? S is the Laplace variable. Fine. Okay. Now, I told that we are talking about 0 initial conditions. So, this y 0 or whatever is there becomes 0. You can remember that when we were taking the Laplace transform of a derivative of a signal yt, then it was becoming something of this shape, but when we talk about transfer function, then we take the initial conditions as 0, because that is the forced response we are interested to check. When we talk about Laplace transform, we are essentially trying to see what is the performance of the system in terms of some input which is being forced to the system. Okay. So, we are not interested to see what are the responses due to initial conditions, we that is why make it 0. Okay. 0 initial conditions are assumed, and then it simplifies the Laplace transform. It becomes 0, then it focus on input output relationships. Okay. As I was telling, it is Z S R, fine. It enables algebraic modeling and frequency domain analysis. In S plane, we can do the analysis, fine, and it provides universal system representation. Okay. The only thing is that when you take a 0 initial condition, it might not be a very practical scenario in all the cases. In some of the systems, initial condition will be there, will be non-zero. So, in those cases we have to check carefully, and I will when I define the limitations of transfer functions, I will come back to these points one by one. Okay. We take another example, second order system. That means the differential equation is now of order 2, fine. So, we have a second order derivative, then constant multiplied by a first order derivative, and then another constant multiplied by the original output or the signal yt. Okay. So, here the assumption is that we have some input ut, we have the output yt, and yt is dependent on ut in this particular fashion, right. Okay. Now, we take the Laplace transform with 0 initial condition approximation. It takes this shape, second order derivative. So, it becomes s square multiplied by ys, then this is ys multiplied by s, and here it becomes omega n square ys, here it is omega n square us, fine. Now, what we do is that we factor out ys this side and we take us here. When we calculate the transfer function, that is the ratio of ys by us, we get this form. So, this is called a second order system transfer function. Okay. We come to see that what can be the transfer function of a drone motor. We have to understand the motor dynamics. When we talk about a typical drone motor, it can be approximated as a first order system. Okay. The motor converts input voltage or signal into a rotational speed, which is omega t, fine. So, we get some input into the system u t, and what we get out of that is a rotational speed, that is omega or omega t. Okay. And when we simplify the first order model, it looks like this. We directly take the Laplace transform here. Okay. So, tau d omega t dt becomes tau s capital omega s plus this omega t becomes capital omega s equal to k u t becomes u s, fine. So, when we derive the transfer function, we have to derive that say this is the output, this is the input. So, the transfer function will be omega s by u s, which is equal to k by tau s plus 1, fine. Now, there is one important concept in transfer function, that is called closed loop transfer function. I was talking about open loop in the previous lecture. So, when we do not have a feedback in the control system, it is called open loop, and that respective transfer function is called open loop transfer function. When we close the loop with a feedback path, then it becomes a closed loop transfer function, fine. Now, you see here we are talking about a negative feedback, right. So, it is a closed loop system with negative feedback. Now, in the case of open loop transfer function, we have seen that this will be the transfer function structure. So, what happens in the closed loop? Fine. We can derive it like this. See, we are getting y t. What is y t? Y t is equal to r t minus this signal. Okay, I will take it in the Laplace domain itself. So, it becomes something like this, y s equal to r s minus this particular term y s into h s, right. Now, this is the error which I was talking about. So, this is the error E s, right. Now, when this error gets multiplied by this transfer function G s, we get y s, which in turns becomes G s into R s minus y s h s, right. So, this is the error signal, and when we multiply it, this is the error here E t, its transformation in Laplace domain is E s, which is equal to R s minus, from here it is y s h s in Laplace domain, right, that we have done. So, finally, what we get is that y s equal to G s R s plus y s G s h s, fine. So, not plus, it is minus, right. So, when we take it this side, it becomes y s into 1 plus G s R s equal to G s R s. What is G s? G s is the open loop control system, but we have now closed the loop. So, now when we see the transfer function, it becomes y s by R s. From here, y s by R s will be equal to G s by 1 plus G s h s. So, if the closed loop open loop transfer function is G s itself, when we come for a closed loop, we close the loop by feedback path, we get the final transfer function or closed loop transfer function of this particular shape. Okay. Fine. Okay. Now, I will talk about poles and zeros. when we have a transfer function, it is the ratio of Laplace transform of the output and Laplace transform of the input. So, we can say that the numerator of the transfer function is a polynomial and denominator is another polynomial, but both are algebraic equations. Fine. So, zeros are the values of a's that makes the numerator of the transfer function 0. That means, if we put this particular condition equal to 0, then what values of a's we are getting are the location of zeros. Okay. Physically, they represent frequencies where the system output becomes 0 for certain inputs. Fine. Okay. Now, what are the poles? Poles are the values of a's that makes the denominator equal to 0. They determine the system dynamics, especially stability and transient response. Please read in details from the reference books. Okay. Now, when we have the idea of poles and zeros, now we will define what is the order of the system. Fine. Order of a system is the highest power of a's in the denominator. Now, where from it comes? It comes from the nth order differential equation only, right. So, from this highest power of denominator, we can get the order of the system. It is n here. Okay. Now, if we have a system like this, then we can say that it is a first order systems, right. If we have a system like this, then we say that it is a second order systems. So, first order system comes from a first order differential equation, second order system from second order differential equation. So, in drone systems, we can we have already seen that the motor speed dynamics can be represented by a first order system. However, we will see in later lectures that when we talk about pitch or roll angles, that means the attitude angles and rotational dynamics gets involved, then we get a second order dynamics, okay, or second order system. Fine. There is another important concept which will be useful in many of the control system topics, that is called the type of a system, which is the number of pure integrators. I will talk about integrators in a later slide, but now we can say that it is a pole at the origin s equal to 0. Okay. So, in the open loop transfer function. Okay. So, the exponent v of s here is the system type. When this is the entire denominator of the transfer function and we make it 0, then we get s power v equal to 0. That means, there are v poles at s equal to 0, then v is the type. Okay. If we have a system like k by s to the power m into s plus 1, then we say that there are 2 poles in this particular system, not 2 poles, there are m plus 1 poles. So, m poles will be at s equal to 0 and 1 pole at s equal to minus 1. Okay. So, this is the definition of type of a system. It shows number of integrator units. 1 by s is denoted as one integrator in the system. I will be covering that topic. Okay. Fine. Now, what is happening here? Okay. Let me erase this one. Fine. Okay. So, why order of the system and type of the system matters? Order influences the system speed. Okay. Then damping and stability will be covered in transient response, all these topics will be covered. Then type determines how well the system tracks input over time. Okay. So, these are very important concepts in control system, and when we talk about transfer function, we have to understand what is the from the transfer function of the system, we can identify or we have to identify what is the order of the system and what is the type of the system. If we are having a transfer function of this type or this structure 1 by s plus 1 by s plus 2 or k, again k, then we will say that there is no pole at s equal to 0. That means, for this system type is equal to 0. Fine. these concepts of order and type becomes very important in transient analysis of the system, control system. So, it will be covered in later lectures, fine. Also you are encouraged to read these topics in details from the reference books, fine. Okay. Now we have poles and zeros. We have defined that when we have the numerator and denominator of the transfer function, if we if for some value of s the numerator becomes 0, then we tell that it is the 0 of the system, and when for some values of s the denominator of transfer function becomes 0, then we say it is the poles of the systems, right. So, s plus 3 is the numerator, making it 0 gives us s equal to minus 3. So, there is a 0 of the system at s equal to minus 3, and then there are poles. If we make this denominator equal to 0, then there are poles at s equal to minus 2 plus minus j 1. So, these are the poles. When we draw it in the s plane, it is something like this, sigma j omega plus minus. So, we have say 1 2 3 1 2. So, we have a 0 at s equal to minus 3. So, this is minus 3 and we have a 0 here, fine. Now, we have two poles in the system, one is minus 2 and j 1, that means this location, this is 2, sorry minus 2 here. So, here we have one pole and here we have another pole. So, this is a complex root. So, it will have one counterpart here, 2 minus 2 plus j 1 is here, and we get minus 2 minus j 1 here, fine. Okay. Now, why are the poles and zeros important? Poles becomes important because at that particular case or at pole Gs becomes infinity. So, we can relate stability here in some way. Then it defines natural response of the system. Poles tells about the natural response of the system, it affects stability, overshoot, settling time, all the performance metrics we are talking about. In the next lecture on transient analysis, things will be clear. Then zeros are the values of s that makes Gs equal to 0. It actually shapes the forced response and can cause cancellations or suppressions of certain dynamics. So, if we want to make a controller with desired performance, 0 plays a very important role in that. Okay. I will talk about some basic systems on system elements and their transfer functions. So, one is gain, it amplifies the or scales the input. If there is an equation like this y t equal to k u t, then k is actually amplifier of the input, right. So, the transfer function in that case becomes k, you can verify. It changes the magnitude of the response without altering the dynamics. Okay. Fine. Then integrator I was talking about. So, integrator is something like this and its transfer function becomes 1 by s. Okay. Fine. So, what we will tell here is that when it becomes 1 by s, what is the type of the system then? Then we have one pole at s equal to 0, then we say that it is a single integrator system. Okay. If we have a transfer function with type 0, then that means that there are no poles at s equal to 0. So, we that is a type 0 system. Integrator itself is a type 1, that means it has one pole at s equal to 0. Okay. It introduces a pole at the origin, fine. Now, differentiator outputs the rate of change of the input that is sensitive to noise. Okay. That is the description. The equation is something like this, y t is the say output and r t is the reference input, then the transfer function becomes something like this. You can remember from the transfer function blocks, or when we have done Laplace transform, we have taken d r t dt, what it will become? It will become s r s and y t is y s. So, from that you can understand why it is becoming G s equal to s. Okay. Please verify. Now, there is another important system which models system latency or time delay. the transfer function is something like this. You try to see this from the time shifting property of Laplace transform, then it will become clear and you can nicely coordinate these two concepts, and then its effect is introducing phase lag, or like introducing phase lag, and sometimes it can make the control system design very efficient or sometimes harder also. Fine. Okay. Visual representation of system components in closed loop systems we have already gone through. This is the reference input, which is the desired output. We have controller, then we have actuator, we have the system, which is in our case drone. We get some output. Now, the sensor tells that whether the output is of desired fashion or not. By feeding back the signal here, we are taking care of negative feedback here. Then this particular signal becomes the error between this input and the sensed output. If there is some error, then controller will work accordingly. It will tell the actuator take this action, then accordingly the drone action will be taken. Okay. Actuator will work in that fashion, so that we get a desired performance from drone. Again, we will check the sensor data, we will feedback, we will check the error, and accordingly the controller will try to give a shape to the desired response of the system. Okay. Each block is described by its transfer functions. Okay. When we are talking about a control system and we have interconnections of different systems, each and every system will be represented by their individual transfer functions. Okay. Fine. Now comes stability concept from transfer function. We were talking about S plane in the last lecture. So, it is a graphical representation of complex numbers in Laplace transform analysis. Each point in S plane is a complex number which has a real part and one imaginary part. Fine. Real part is related to exponential growth or decay, and imaginary part indicates the system oscillation and frequency. This much we have discussed. Now, I am giving you one interesting idea here. I am telling that when the sigma is greater than 0, then it leads to instability. That means, the system with this kind of sigma greater than 0 will become unstable. Okay. So, the system poles, when we plot at the right hand plane, this is called right hand plane and this is called left hand plane. We do not want the poles of the systems to be on the right hand plane. This is something which we do not want. Okay. So, the poles which we denote by this small cross sign should be ideally at the left half plane, and that gives a stable response. Right half plane is a region of instability. But what happens if the pole is on the imaginary axis, something like this, like this, like this, then what happens? It is called a marginal stability scenario or sustained oscillation scenario. That is not unstable, but from the stability point of view, that is also not desirable in many systems. As I was telling in the altitude hold problem, that when the drone is coming up and taking a height h, it should maintain this height. If it is oscillating here without getting stabilized or holding the altitude properly, if it gets oscillated like this up and down, that is not something desirable for a particular application. Okay. So, when we are designing a control system, we will try to keep the system poles, the final transfer function with all the interconnection of different building blocks. When we get the final transfer function, it will be ideal if we can place the poles of the final system into the left half plane. It can be on the real axis, it can be complex, that is a different story, but to avoid instability, the poles should be in the left half plane. Okay. Fine. So, if you see here the pole locations, if we place in the left half plane, then we see that it will give a stable region. If we put it in the right half plane, which is designed like here, we are denoting it as a red block, that means danger, it is an unstable region. And on imaginary axis, if we are having poles, then we can say that it is not as dangerous as the unstable region or instability, but it is not as safe as the stable region also. So, we call it as a marginally stable counterpart of the system. Okay. Fine. Now, what is happening here? We are putting some poles in the right half plane. What it will give us? It will give us some unstable behavior of the system. The response of the system will become something like this. So, it is a kind of growing oscillation. Why oscillation? Because of this imaginary part and the real part becoming positive will give a growing oscillation. Whereas, for the left half left half plane poles, the system response will take a decaying oscillation kind of thing and finally it will settle down. So, it is like going towards equilibrium and that is what is desirable. So, the poles on right half plane gives unstable behavior colored in red to show the danger. Poles on the left half plane will give stable behavior. Okay. Poles on j omega axis, if the poles are on this, then it will give a kind of sustained oscillations, okay, keeping kind of the same magnitude of omega. Okay. If the poles are far left, then like here, then it will give fast response and the damping will be high. So, all this analysis of transient system performance, stability, these concepts can be analyzed with different concepts, mathematical tools like Routh-Hurwitz criterion, Nyquist criterion, root locus analysis and so on, but these are not the scope of this particular lecture. Okay. What are the limitations of transfer function? It is applicable only on linear time invariant systems. So, if the system becomes non-linear or time varying, it will not work. Fine. No direct representation of internal states, and that is why it does not consider the initial conditions also. It is assumed that the initial conditions are 0. You can remember that if 0 or something we are talking about 0, and also it cannot handle multiple input and outputs. So, it can't handle MIMO systems, but it works only for CISO. Okay. Single input, single output. So, if a system is having multiple input, multiple outputs, then we have to individually take from one input to one output and then we have to define the transfer function. But in that way, there will be having like a mapping from each input to each output and there will be individual CISO transfer functions, but that makes handling the system a bit complicated. So, that is one limitation of transfer function. So, what do we study here? We see the basics of transfer functions, we define the transfer function, we see that how it is mathematically represented, we understand that what is the importance of Laplace transform in defining transfer function. Then we see how to derive transfer function from differential equations. We talk about open loop and closed loop transfer functions. When open loop it is easy GS, when closed loop it becomes GS by 1 plus GS HS, where HS is the transfer function of the feedback path or feedback loop. Then we talk about poles and zeros, their significance. We talk about order and type of the systems, which are very important for performance analysis of a particular system. Then we talk about basic systems with their transfer functions like gain. Then we talked about integrator, we talked about differentiator, we talked about delay based systems and all. Okay. We talk about S plane, how we can divide S plane in terms of stable region and unstable region. In the right half plane, having poles will give unstable behavior of the system. Left hand side will give stable behavior, and if the poles are on the imaginary axis, then there will be sustained oscillations, and that situation is called marginal stability. So, with that, this lecture is concluded. These are some reference materials. These are some MATLAB resources which you can go through, so that coding in MATLAB becomes easier. Thank you. See you in the next lecture.